like bacteria in a petri dish. The force goes through, the particles try to head towards it, and then once it's gone, they then re-establish their distance from each other. The keep apart comes into effect, and the particles push each other away from each other. So there you go there. So that's actually quite cool. Now, this actually wouldn't happen if we didn't have this cylinder being used as a collision. If we actually go to the collision operator, which you see we have here, and turn it off, and I'll just turn off this gravity as well. And you can see that if we press play, you can see the particles are created and they push each other out, and eventually they settle down into a steady state. But if we actually go to the keep apart operator here, and we change to absolute size, which you can see we have here, if we make a much bigger fall off zone, the particles will now keep on pushing. So basically this cylinder was used to actually keep our particles within a certain area. And you can see there we go, our particles keep on pushing outwards. And if we look at it here from this angle, you can see they're pushing outwards. And after a while, you know, they're all actually birthed originally on a horizontal plane. And that kind of gives us an artificial result in some respects, because after a certain amount of while you get rounding errors that pop in. And this is quite an interesting feature actually. And you'll see that after a while the particles start to displace each other in three-dimensional space. You can see they're pushing each other apart in three-dimensional space, so they're pushing each other out there. Once they've reached their fall-off zone, the drag operator stops them pushing any further, and they come to a rest. So you can see there you go, they're pushing each other out, and then they come to a rest there in that little field. So to see it maybe in a little bit more of a sort of natural environment, we'll create a sphere, and our particles will now be born within that sphere, and then they'll push each other apart. So there you go, you can see they're all pushing each other out. Some particles are being pushed inwards and some particles are being pushed outwards. And eventually, again, they reach a steady state where they pretty much come to a stop. If we put them inside the volume of the sphere, and I'll press play again, you can see, again, they're pushing apart from each other. And eventually they come to a rest. And again, I can turn on our force, and they never actually come to a complete rest before the actual force pops through, but you'll see, again, they come to a rest, pretty much. And then our force flies through and it perturbs them, and they fly around a little bit more, and again they come to a rest again. So that's the keep apart operator. A very interesting operator because, you know, as I said, if you combine a number of keep apart operators, using some of them with very weak forces, you know, using a force of maybe 2 or 3 to drag particles together, which is pretty much how gravity works. And then gravity works over very long distances, you know, our sun has a gravitational effect on us. Then you can use very strong forces, values of say 20 or 30, but with much smaller core radiuses and fall-off zones, and that can then act as a more like a magnetic force. Magnetic forces are much stronger, but they have a much higher fall-off. So, you know, if you've got a magnet where the sun is, it's not really going to have any effect on us. I think in absolute terms, you know, if you look at it in terms of physics, it's possible that that magnet next to the sun maybe does have an effect on us, but it's very, 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 very weak, to the point where it's completely unnoticeable. Whereas the sun, you know, it's many millions miles away, does have an effect on us. So you've got those two different forces to think about. You've got gravity and you've got magnetism. And you can actually simulate both of those forces by using the keep apart operator, by either using weak forces over great ranges, gravity, or using strong forces over very short distances, which you have with magnetism. And then, you know, you've got more control over exactly how that force field is actually implemented in the scene, whether it's got a very hard center to it, within which, you know, you get then particles bouncing off each other almost as if they've got some sort of solid mass to them. Or you can make the particles into like much larger fields, which we're actually doing here in this example. So, you know, if I do a fall-off range of 20, you can see our particles will just keep on pushing against each other They just keep on pushing out and out and out because they've got this massive fall off zone, so the force can have effect out to a very large distance. So that's it for the keep apart operator. Have a go with it, have a go with our example, and try out different options with it, and you'll actually see, you know, it's a very interesting operator. You can do lots of different results and effects with it. So it's well worth trying out some of the effects that you can get with it. You know, it really does bear a lot of experimentation. You can see, you know, in this particular case I've used a very particular orientation using this collision cylinder and using forces, and you're getting very interesting results with it. You can try doing similar things with particles inside a volume and have them pushing off each other with a negative with a positive force, and then you can have weaker forces pulling them together, and you can try, you know, simulating clouds of gas by using this particular operator. So it's a very interesting operator and well worth experimenting with.